So let's start today's class. So today we'll be discussing about the real gas equations and all. But before that, let me just briefly discuss about the thing that we have done in our previous class. And so last week we have discussed about the Brownian motion. So let me just briefly tell us about what it is. So Brownian motion. So we know that first we discuss several properties of Brownian motions. So it has property like it is a completely random motion. Okay. So complete random motion where two particles motions are not related at all. When if there are two neighboring particles, okay, both of their there is basically no correlation between the motion of each of those two particles. We also discussed that for smaller particles, greater the motion. So what is the reason behind this? The reason behind this is, let's suppose in a solvent medium we put some Brownian particles. Okay, so let's suppose it's a big size. Let's first in the case one, let's consider it's a big size Brownian particle. So it will face the random forces from different types of directions, and since it's a big particle, so each of the force component will cancel with each other, and because of that the net force that would be acting onto the particle will be very small. So if net is very small, okay. But in case of a smaller particle, since the particle size is small, it will face like all the components of the forces will not be cancelled with each other. So there should be some asymmetrical force that would be acting onto the particle, which basically the reason for showing the Brownian motions. So because of that, the F net on the smaller particle will be higher. Okay. So this is our second property. Third one, we have discussed that it's very dependent. It's dependent on viscosity, because viscosity basically it's a property of the medium over which the Brownian particles basically move. So during the random motions, if the friction is very high and the viscosity is very high, that means the particle will face high resistance, right? So because of that, the motion would be smaller, right? And if the viscosity is small, so that means the frictional force would be also small, and the particle, because of the randomness, the particle will move at a greater distance. Okay. Fourth property is for higher T, motion is greater. Okay. The reason is basically this Brownian motion is kind of eternal motion. Okay, so it basically the energy for this Brownian motion comes from the thermal energy of the particle, and thermal energy of the particle is directly related to the temperature of the system. Okay, so if you make the temperature higher, so that means the particle will face higher forces. So because of that, the motion will be also greater. Okay. These are the several properties of the uh, of the Brownian particles that we discussed in the last class. Also, we have discussed that the MSD, about MSD. So what is MSD? MSD, from the, as the name suggests, it's basically the mean square displacement. Okay, so you have a particle, you tag the Brownian particle. With time, it displaces distance, like let's suppose x1 to x2, x3, like this. So it travels through these distances. So in order to calculate the MSD of this particle, what you have to do, you have to basically square all of the distances, x2 square, x3 square, like this, up to the nth order of observations. And after doing the square, it basically do the mean of this, mean of all the displacement. Okay. This basically gives you the MSD. Yeah. This basically gives you the MSD of the particle. Okay. Now, so between each of the displacement, the time interval that we took, that should be fixed. That time interval we have denoted with by tau. Okay, tau. The tau is the time scale that we have to define. Okay, between each of the displacement. Okay. Now, so if you can calculate the MSD and this time interval tau, so from these two measurement actually you can calculate the diffusion constant of the particle. Okay, so diffusion constant D, Einstein basically shows this relation. Okay, so Einstein relation shows that the diffusion constant of the particle, that is D, is equal to r square by 2 tau. R square is basically the distance traveled by the particle. Okay, so this is the square of the distance. Okay. Basically the MSD you can say. Okay. Now, there is another proof of this diffusion constant that can be done using the concept of the osmotic pressure. Okay, so osmotic pressure, you know, if you basically if you like there are two in a compartment. Let's suppose there are two sides which are basically connected by a permeable membrane. Okay, let's suppose in this case you have a solution, and in this case there is only solvent, like only water, let's suppose. Okay, and in this case there's some water plus some particles. Okay, solution. So because of that, there would be osmotic pressure that would be there in this membrane, right? That osmotic pressure expression you know, equal to N kBT. And from this concept of osmotic pressure, okay, osmotic pressure, Einstein, so using this concept of osmotic pressure, also Einstein derived the expression of the diffusion constant. So that expression is basically given by D equal to ABT 6 by eta R. Okay. Major thing here is that here R is the radius of the particle. Okay, so we are considering that the particles are basically spherical in shape. Okay, so the radius of the particle. Okay. Now, if you compare these two equation 1 and 2, that basically gives you. So if you compare equation 1 and 2, so this gives you r square by 2 tau equal to ABT into 6 by eta r. Or you can write it like this also, r square equal to RE by NA. KB, you can break the KB into R by NA, right? So R by NA into 1 by 3 pi eta R tau. So this is known as the, or this relation, both of these relation, basically known as the fluctuation dissipation relation, where the R is the MSD. So because of the Brownian motion, the particle basically fluctuates, right? The position of the particle basically fluctuates. So that fluctuation basically quantified by the R square, or the MSD thing. And since the particle moves in a medium, and the medium has a viscosity, so because of the viscosity, there will be friction acting on the particle, and it basically dissipates the energy of the particle. Okay. So eta is basically acting as a dissipation, okay, the friction of the particle. So since this fluctuation, this MSD basically gives the fluctuation, and eta, this is dissipation, both these two things are related using this relation. So because of that, we are telling this equation as a fluctuation dissipation, FD duration, okay. Lastly, we have discussed about what is the concept of sedimentation. Okay, so what happens that if you, let's suppose in a water beaker or any water container, if you put initially some Brownian particles inside this water container, okay, after, so each of the particle uh, will be facing some gravitational pull, right, mg. So because of that, the particle will try to sediment. Okay, so there will be a inhomogeneous distribution of the particle. Okay, it's like the deeper the particle, deeper into the container, the particle density will be higher compared to the upper part of the container. Okay, so that means the distribution of the particle will be follow some certain distribution law, right? And also the pressure. Okay, that will mean the distribution of the concentration of the Brownian particles. Okay, and that relation of the distribution of the Brownian particles, we have written that distribution as n equal to n naught into e to the power minus mgz by rp, where at z equal to 0, that means in the bottom the particle number would be n equal to n0. So that is the initial, like the boundary condition, you can say. Okay, and this is the distribution of the particle at a particular distance z. Okay, now from this relation actually, or by using this, by doing this experiment, Perrins basically calculated the Avogadro number of particles. So actually using this relation, by rearranging some terms, you basically write the Avogadro number. Okay, Avogadro number NAS 3RT by 4 pi RQ rho minus rho time into G into mm m0 by n. So from an experimental point of view, if you can calculate all of this quantity of this relation, the quantities from the right hand side, if you put it into the relation, you will be basically getting the Avogadro number. So Perrin actually basically did this experiment, this sedimentation experiment, and he basically verified this Avogadro number in a 6.02 into 10 to the 20th, and because of that he got a Nobel Prize. Okay. Okay. And so this is the thing that we have discussed in the last class, and after that we have also solved some problems. Okay. Now for today's class we'll be talking about first we'll be starting from the specific heat. Okay. Specific heat of, you can say, gases. So gases or solids. Okay. So previously actually I've discussed in the earlier classes about specific heat of gases. So now we will be mostly considering the specific heat of solids at first. Okay. So specific heats. So initially, experimentally, what it has been it has been observed that uh, the specific heat of solids actually at a room temperature. So at finite temperature or room temperature, you can say room temperature. Experimentally, it has been found out that the specific heat of most of the solids has the particular value C as 25 joule per mole inverse Kelvin inverse. Okay, this is the specific heat of the most of the you can say solids or most of the elements. Okay, that has been observed at room temperature. So to explain this, first explanation has been shown by the Dulong. So that is known as the Dulong-Pettit law. Okay. So he has basically shown that that in solids, basically atoms or molecules has thermal energy, right? Thermal energy. Okay. So so because of that, the molecules can vibrate, right? So number of vibrations, so the total number of, so if the molecules vibrate along with the other degrees of freedom, that is rotation or translation, right? So the total degrees of freedom of a per molecule is basically given by 6, right? Now we know that each of the degrees of freedom from the equipartition of the energy, we know that each degrees of freedom basically contributes half kBT of energy, right? So for this case, for a particular atom, so energy per molecular atom, whatever it is, the energy would be 6 into half kBT, and for 1 mole it would be multiplied with Na, since Na numbers of molecules or atoms are there in the particular substance, right? So Na into 6 into half kBT. Okay, so that would become 3R2. Okay, because Na into Kb equal to gas constant R. Okay. Now if you calculate the CV, you know this is basically the U, that is the energy. CV or it's not CV, let's write it as C. That's the specific heat. Okay, so C is basically GU by GT, that is 3R. Okay. And 3R is what? 3 into 8.314, like joule per mole inverse Kelvin inverse. So calculate this, it will give you roughly 25 joule mole inverse Kelvin inverse. So in that way, this Dulong-Pettit rule basically gives a physical or mathematical explanation of how this specific like how the most of the substance shows this particular value as a specific heat at room temperature. So in that way, at a particular range of temperature, this basically law validates. Okay, but the issue begins at the lower temperature. Okay, so because experimentally what has been observed is that the specific heat is basically temperature dependent. Okay, so if you basically lower the temperature, experimentally it has been found out that the specific heat follows, suppose in this axis you plot Cv by R, in this axis if you plot the temperature, the specific heat follows basically this kind of a plot. Okay. So this is the 3. 3 means here specific heat of so at a particular temperature, let's suppose this particular temperature is varies for different substance or different types of molecules. So at a particular temperature only, this CV attains this value 3R. Okay. But if you decrease the temperature, it basically the CV follows a TQ t to the power cube type of a plot. Okay. So this what we have explained to Dulong-Petit draw is only valid into the higher temperature regime. Okay, but in lower temperature regime, this CV basically follows that t to the power cube kind of a law. Okay, which basically is not being explained by this Dulong-Petit rule. Okay. Now to explain this property of the specific heat of the solid, Einstein basically uses the some concept from the quantum mechanics, or more specifically from the black body radiation. And using that concept, he basically tries to explain this kind of behavior. So, what he proposed that uh, so before that, let me tells you what this black body radiation is. So so this black body radiation is basically, because this concept of black body radiation is basically used by Einstein to explain the nature of the specific heat for the solids actually. So what black body radiation basically tells us that in a so this radiation basically consists of uh, photons. Okay, so this radiation basically consists photons, which the Planck actually named this photon as quanta of energy. Okay, quanta of energy. Okay. So this quanta of energy has an analogy with the quantum harmonic oscillator. Okay. So this each quanta of energy, this photons, basically has energy of quantum harmonic oscillator. Okay, that is given by basically n h cut nu. Okay. NH nu. Okay. So 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 if you consider like each of the photon can have energy of nh nu, then using this thing you can basically calculate the average energy of each of the photon. Okay, that is E bar. So this can be mathematically calculated in quantum mechanics. So that expression of E bar basically given by h nu by to the power h nu by kt minus 1. So this is the average energy. Okay. Now this is the average energy for black body radiation. Okay. Now basically Einstein, for his explanation of this specific heat, he uses basically this expression of average energy. Okay. So what he proposes is that uh, each of the atom, so Einstein theory of specific heat. So what he has formulated is that each atom vibrates with same frequency nu. Okay, about this main position. So all of the atom in the solid basically vibrates with the frequency nu due to the thermal energy, as you know. Now, so each DOF, each degrees of freedom of the molecule, has this exact form of the energy. So E bar is basically h nu by to the power h nu by kt minus 1. This is the basically average energy per DOF. So each degrees of freedom contains this much of average energy. So in that case, the total energy would be 3 into Na into E bar. Okay, so that would gives you, if you do the calculation, if you took h nu by kt as x, then this whole expression becomes 3 RT into e to the power, sorry, x into e to the power x minus 1. So this will be the total energy of the particle. Okay. So that means that, so basically what Einstein did is that, so he considered, like, because of the thermal motions, each of the particles uh, moves or vibrates with the same frequency nu. Okay, and what would be the average energy of each of this molecule? So in order to derive that, he uses this concept from black body radiation from quantum mechanics. So this energy he is taking as the average energy of each of the degrees of freedom, for each per degrees of freedom of the particles or molecules, and from that by multiplying with Na, the total energy for one mole, obviously for one mole, let's say total energy is for one mole. So for one mole, the total energy would be 3 Na into E bar. So so now for one mole of the solid, you can calculate the specific heat. So let's take it as Cv. Cv means specific heat at constant volume. Okay, so when you do the derivative with respect to the time, just take volume as a constant. So if you do that, the derivative of this quantity basically E, that is 3RT by x e to the power x minus 1. Okay. Now since you know x is also dependent on the temperature, so you have to also do the derivative with this on x also. So after doing that, the expression will become like this: 3r into x into e to the power x minus 1 plus t into 1 by e to the power x minus 1 minus x into the power x to the power x minus 1 whole square into dx dt. Okay. This is the full expression of the specific heat at constant volume. Now, so yeah. So now you can further simplify these calculations. Okay, so because it's everything is written in terms of x. Okay, so what you can do, there is dx dt, right? So x is basically h nu by kt, right? So dx dt, you can write it as minus h nu by kt square, or more formally in terms of x, you can write it as minus x by t. Then you substitute this dx dt thing here. After doing that, you are getting Cv equal to 3r into x by e to the power x minus 1 minus x e to the power x minus 1 by doing some simplifications, plus x square e to the power x by e to the power x minus 1 whole square. Further calculation algebraic gives you x square e to the power x by e to the power x minus 1 whole square. Okay, so this is the final expression. Okay, yeah. So this is the final expression of the specific heat. Okay. Okay, so here you can, as you can see, so it's clearly dependent on to the temperature. Okay, so x we know is h nu by kBT here, h nu by kBT. So it's definitely dependent on to the temperature of what is temperature of the molecule or the or the particle. Okay, of the solid. Now, we will be consider two of the extremum cases. In one case, the temperature would be the higher. In one case, the temperature would be smaller. Okay. Okay. So before doing that, let me define one quantity that is, like in literature, it is defined actually. So that quantity is known as the Einstein temperature. Okay. So this equation is known as Einstein's equation for specific heat of solid. Okay, this is known as Einstein equation for the specific heat of solids. Okay. Now you can define a temperature that is known as the Einstein temperature. So that definition is basically theta E. So theta E basically denotes the Einstein temperature that is given by h nu by k. Okay, and x you can write. So instead of writing everything in terms of h nu by k, you can write x as theta E by t. Okay. So that is basically a ratio ratio for ratio between Einstein temperature and the temperature of the system. That this X thing is basically. So now we'll be considering two cases. Okay, so in first case, two extremum cases. Okay, that we have discussed. The first case would be the high temperature case. Okay, so high temperature means the temperature of the solids would be much higher to the Einstein temperature. Okay, that means the X that is defined as theta E by T is much smaller than 1. Okay, so that means we can take the limit of X as tends to 0, right? So if we put, so this was the expression. Okay, so CV is basically 3R into, let's write this whole function as EX, this whole function as EX. Okay, so 3R into EX, so where EX is basically x square e to the power x by e to the power x minus 1 whole square. Now for this high temperature limit, the x is tends to 0. So limit, so you have to evaluate what would be the limiting case of e to the ex of this function ex at the limit x tends to 0. So we will basically derive this. So in the limit x tends to 0, this function x square e to the power x by e to the power x minus 1 whole square. So if you do, you basically expand this e to the power x into the as a power law, higher order of x, then divided by this series of 1 plus x by x square by 2 factorial and all, at the limit x tends to 0. After doing all of this thing, you will be getting something like x square by x square, which is basically 1. So that means in the limit x tends to 0, the CV basically retains the value 3R, right? That is nothing but the Dulong-Petit law, right? That is nothing by 25 joule per Kelvin inverse mole inverse. Okay. So for high temperature case, as you can see, this Einstein assumption basically matches with the experimental result. Okay, so in that way, for the high temperature limit, the Einstein formulation is successful. Okay, but next we will be considering the low temperature. So for the low temperature case, for the low temperature case means low temperature case. In that case, the T is smaller than the theta E. So X, that is theta E by T, would be greater than 1, or that means X would be tends to a very high value. For this case, we will consider it as a very high value, tends to infinite, or you can say very high. X is very high, very high. Okay. So now we put the limit onto this function e to the power ex function, likewise what we have done for the high temperature case. Okay, so if we put it in, so ex is basically x square e to the power x by e to the power x minus 1 whole square. Now since x is very high, so e to the power x would be also very high, much higher than the 1. By substituting this limit, this whole expression basically took the form like this, x square e to the power x. Now if we put it in, the CV expression will become asymptotically become 3R into x square e to the power minus x. Okay. So that, as you can see, so CV is basically dependent upon the exponential of the minus of t. Okay, and by so x is basically 1 by t, theta by t into 1 by t whole cube. Okay. So CV is the relation of CV set. This is for low temperatures. One is low. For the low temperature case, as you can see, CV basically related with the temperature by using this relation, where like both the exponential and this the minus 3 terms of minus 3 exponent is there in the power of t. So, as you can see, experimentally what we have observed is at lower temperature Cv is proportional to basically Tq, right? But here the relation is a bit different. It's kind of exponentially related. So although it's kind of if you plot a diagram, it's basically looks like this. Cv with respect to the t. It in a like approximate way, it basically follows what is experimentally we have observed, but it's not basically giving the t to the power q format. Okay, that experimentally got. Okay, it gives you exponential kind of a e to the power minus theta a by t. Okay. So it gives you a kind of exponential type of relation at lower temperature. Okay. So in that way, the Einstein formulation is not that much rigorous in the limit of low temperature. So now basically now after this formulation, there is another theory that is basically given by Debye. So that is known as the Debye's theory of specific heat. So Debye basically gives kind of a more refined version of this Einstein theory. Okay. So what Debye basically postulated is that. So next is the Debye theory of specific token. So what Debye postulated is that. So compared to Einstein, where we have only considered the molecule has a singular frequency that is given by Newton. But here, Debye considered the solid as a continuous elastic medium, where instead of a monochromatic frequency, it has a continuous spectrum of frequency. Okay. So what we have considered is that the solid is a continuous elastic medium of lattice vibrations. Okay, and their vibrations are kind of acoustic type. So these are elastic acoustic type of vibration. Okay. And second is that the vibration is not monochromatic. Okay. So it has basically it has a continuous spectrum of frequencies. Okay. Continuous spectrum of frequencies. Okay. And up to a maximum of so it's like frequencies are distributed, but the distribution is not stretched up to infinite. So it has a higher limit. The distribution has a higher limit. That limit is basically given by Newton. So this is the basic difference between Einstein and Debye's theory. Okay. So now by considering these facts or these these formulations, so there are two kinds of modes. Okay, since these are acoustic types of vibration, there are two kinds of modes. Okay, one is the longitudinal type. Okay, so this is two types of modes. Okay. Types of waves. So basically waves moves like this. Okay, so when waves moves like this, acoustic waves, it has two types of you can say two kinds of waves. Okay, so one is stretched along the along these longitudinal directions. So these basically give single mode, and another is from this direction. So okay, the perpendicular to the direction of this longitudinal. These are known as the transverse waves. Okay. There are two modes of the transverse wave and one mode of around the longitudinal. So two types of waves. One is the longitudinal and another one is the transverse wave. And this has single mode, one mode. As you can see here, it can only move along this side or this side, so it has only one mode. And here it has two modes. Okay. As you can see, this has basically two different plane. It can go to different axes. It can move. Okay. This has this transverse wave, basically two modes. Okay. Now if you calculate what is the range, what is the number of independent modes for each of the type. Okay, so for longitudinal type, the number of modes would be XL equal to 4 pi number of modes in between nu to nu plus d nu. So in this range, the number of nodes would be so let's suppose the volume of the total solid is occupied by V. So 4 pi nu square into nu square d nu into V into CL cube. Okay. CL cube is nothing but speed of the longitudinal. Okay. Speed of longitudinal wave. Okay. And this is the number of modes. Similarly, for transverse type, the number of modes would be 2 into 2 comes because transverse we have two types of modes, right? So 2 into 4 pi nu square d nu into d by ct cube, where ct is the speed of transverse wave. So now, okay. Yeah. So now, so you know there is a maximum limit of this. So now, so the basically the density. So the density basically given written by so g nu d nu basically written by XL. Density is nothing but the number of wave that is between nu to nu plus d nu, right? So the total number of waves. So that is we are denoted as g nu d nu. G nu d nu is basically given by XL into X tau, the total. XL into XT, sorry. That is basically given by 4 pi V into 1 by CL cube plus nu cube CT cube by nu d square. Now, if you integrate it from 0 to mu d, g nu d nu, it would give you the total number of degrees of freedom. That is Na is total number of molecules into G. Okay. Hello, hello. Okay. So, so if you do the integration of the density of state from 0 to nu d, the maximum, it will gives you the total degrees of freedom. Okay. So if you do the integration, so this would be 0 into nu d into 4 pi b into 1 by cl cube by 2 into c t cube into nu square g nu into 3 na. Do the calculations and all, if you do it, you'll be getting nu d cube as 9 na into 4 pi b into 1 by cl cube plus 2 by ct cube. Okay. So this is basically the expression of this nu d. Okay. So nu d is basically known as the debase frequency. Okay. So nu d, this maximum limit of frequency that these solids can attain, this maximum limit is known as basically debase frequency. Okay. This is the expression you can say of the debase frequency. Now from here you can calculate also the total energy. Since once you get the density of states, from that quantity you can calculate many other things also. First you have shown to calculate the debase frequency. Next thing that you can calculate is the total energy. So total energy is nothing but E into average energy E bar into density of state dV. Okay, 0 to nu t. But average energy is nothing but you already know, that is given by this black body radiation. Okay, E bar equal to h nu by kt minus 1. Okay. So if you do this, so the calculation looks kind of this kind of form: 1 by CAQ plus 1 by CTQ 0 to nu d h nu cube by e to the power h nu by kt minus 1 d nu. If you do all the calculations, and if you take if you do some substitution like x equal to h nu by kbt and xd equal to h nu d by kbt, you'll be getting the expression of cv as cv, that is d dt, as cr some function of theta d by t. So from the construction itself you can know. So here theta d is nothing but the debase temperature. Okay, just like we have defined Einstein temperature, so theta d is debase temperature, which is the expression is here h nu d by t. Okay, and xd is basically defined as theta d by t. Okay, the similar way, similar construction that we have followed in Einstein formulation actually. Now this functional form of the theta d basically looks like this actually. Okay, so if theta dt basically looks like this: 12 into xd cube by 0 to xd x cube. This is a big expression actually. Q by x minus 1 dx minus theta xd 3xd into e to the power xt minus 1. Okay. So this is the expression. Okay. So yeah. Okay. So now okay. So now here also we'll be considering two of the cases, right? So one cases would be the high temperature case and one case would be the low temperature case. Similar the way we have done for the relation for the Einstein case. Okay. So for high temperature limit, high temperature limit where T is much greater than theta d. Okay. So in that case, xd, that is defined by basically theta d by t, would be smaller than 1. So x basically tends to 0. So in that case, we can write this e to the power x equal to or approximated as 1 plus x. So basically ignores the higher order approximation of x. So in that case, this integral, this fx that we have defined as this thing basically, this f theta dt, or in terms of x also you can write. So this basically takes a form or approximated as a form as x d cube and x 0 to x d x cube dx into 1 plus x minus 1 minus 3xd into 1 plus xd minus 1. So it will become 12xd cube into xd cube by 3 minus 3. So it will become 4 minus 3 equal to 1. So fx basically becomes 1. So that means fx is 1. So from this expression you can tell Cv is equal to 3R, that is very known thing to us, that is 25 joule per mole inverse Kelvin inverse. Okay. So high temperature limits, as you can see, this expression basically this expression basically matches with the experimental results. Similarly, for low temperature case, if you observe, if you derive this expression, so for low temperature limit, that means if t is much smaller than theta d, so in that case, what basically happens is that, so xd is basically theta d by t. So as t tends to 0, that is very small, xd basically tends to infinite. If you put this thing, so if now the fx, this function, basically the integration inside the function will take a limit from 0 to infinite, right? So x cube dx by e to the power x minus 1, and the other part will become 0 since this is to e to the power x, this thing also will be increased since x tends to infinite. So this, because of this whole thing, this denominator of this function will become very high. So that's why this whole thing will become very small, this whole expression. So this second term will become close to equal to 0. Now if you do the further integration, there is some specific technique of integration. If you do that, you will end up with, for t tends to 0 limit, the Cv basically takes a form like this: 12R pi to the power 4 into pi 3 theta d cube by t cube. So you can see Cv is basically proportional to t4. So that is exactly the functional form that is required to explain the experimental results. So that we basically got by using this Debye's explanation, which is basically not there in the Einstein explanation. Okay. So in that case, we can say the Debye's theory is basically a very very well-known theory that basically can well explain the behavior of the specific heat of solid, both in the case of high temperature as well in the case of low temperature unit. Okay. So this is basically a well accepted theory. Okay. So this is known as the Debye's T cube law. This law is basically known as Debye T cube law for low temperature. For lower temperature. Yeah. So now, okay. Now in the next part of the discussion, we'll be discuss about the behavior of the real gases. So far we are only dealing with the ideal gases, okay, where we do not consider any kind of interaction with the walls. We do not consider any volumetric effect, like the particles we are considering as point particles. So it does not, the particle does not contain any kind of volume. So there is no basically excluded volume in the assumptions. Okay, so that is the case for the ideal gases, but in the real life the gases are different. Okay, so the gases basically interact, right? It's the molecules, and the molecules also have their own radius, they have their own volumes. So all of these things, if you consider into your theory, in that case the expression of the real gas would be different from the expression of the ideal gas. Okay. So before that expression, let me just let just discuss some of the properties of the ideal gases. Okay. So, or you can say the behavior of the real gases. Okay. So behavior of the so if you observe the behavior of the real gas, so it kinds of like that. So in the case of ideal gas, we know it follows a very simple relation, which is given by PV equal to energy, right? Or PV equal to NPTEL. Okay. Now, so this from this relation, as you can see from this relation, you can see the for a constant temperature, PV is basically fixed. Okay, if T is constant. Okay. Now, so that means if you change the pressure, the PV expression should become linear. So it just takes a particular constant value at a particular temperature, so it should remain constant, right? But in experiment, it has been found out that it is not really constant. Okay, this is the ideal behavior. But experimentally measured, this PV quantity, if you change the pressure, the experimentally gas kind of shows this kind of variations. Okay, this is for CO2 gas, this is for O2 gas, something like this. It's made here. This is for H2 gas. Okay. These are the kind of curves that experimental measured. Okay. This is, you can see, this is this is basically not aligned with the ideal behavior. Okay. Deviates significantly from the ideal behavior. Okay. So similarly, there is also experiment where they have this is called the Amagat experiment. This experiment has been done on the carbon dioxide gas. Okay. So in that experiment, what they have done is that they have plotted the pressure and the volume of the CO2 gas. Okay. So ideally, this is the P and the V. So ideally, the P and V is related by P equal to KT by V, right? Or P is basically a relation to proportionally relation with 1 by V. So So the ideal gas behavior will show some kind of a hyperbolic kind of a curve like this. Okay. This is the ideal gas. Okay. But experimentally for the carbon dioxide gas, for different temperature, it has been found out that at a higher temperature it kinds of shows this kind of ideal behavior. Okay, but if you lower the temperature, okay, it shows this is let's suppose theta 1 degree centigrade. If you lower the temperature enough, it shows this kind of behavior. Theta 2 is smaller than theta 1. Is it more? It will become this. Okay. So why this curve flattens out here, and it is also well deviated for the ideal case. So as you can see, depending upon the temperature, so the gas behavior of the ideal gas, behavior of the real gas deviates significantly from the ideal gas law. And here you can see there is this plateau kind of region. The reason between this plateau region at this point between C and B is that for this particular temperature theta 2, and if you increase the pressure high, that is in the y direction, what basically this gas happens is that the gas basically condensates. Okay, so this basically gas becomes fluid like. Okay. So this is the condensation is happening. Condensation is happening here. So from the ideal gas law, all these things cannot be explained. Okay. And there is a critical temperature to get this condensation actually. Okay. So that critical temperature is basically the temperature where the condensation just begins. Okay. So where you just got this plateau curve. First, this is the, let's cover the theta C. That is the critical temperature. Okay. So at that critical temperature and at that particular pressure, which is known as the critical pressure, this condensation just starts. Okay. So let me write the definition of this critical temperature into the pressure. Okay. So Tc is the critical temperature where above the critical temperature or gas cannot be liquefied no matter how high the pressure is. Okay. As you can see, if you make the temperature higher than the critical temperature, you can see there is no plateau region basically arrives. That means if you increase the pressure more and more, still there is no condensation will happen until and unless you hit the critical temperature or you hit lower than the critical temperature. This is the critical pressure of a gas at Tc. Okay, so Tc is basically this temperature, this pressure, okay, this pressure Tc. Okay, this pressure is known as the critical pressure. Okay. And last is the Vc, that is the critical volume. So volume occupied by 1 mole of gas at Tc and Pc. So at Tc and Pc, the volume of that 1 mole gas is basically denoted by Vc, the critical volume. Okay. So So these are basically some of the properties of the ideal gases. Okay, so sorry, not ideal gases, real gases. Okay, so where you can show this kind of phenomena where PV diagram basically deviates from its ideal behavior, and also if you decrease the temperature and increase the pressure after a particular critical temperature, increasing the pressure results the condensation of the gas. Okay. So to basically characterize that, we have defined these quantities: this critical temperature, critical pressure, and critical volume. So now to basically predict or basically explain this behavior of this real gases, uh, Van der Waal basically states this new equation of state that is for the real gases. Okay, and for his equation compared to the ideal gas, he considers several things. Okay, real gas, additionally considerations, you can say considerations. So for the case of real gas, what are the things Van der Waal considered is that one is hard sphere. Okay, so he considered the real gas basically made of hard sphere. Okay, of finite size. Okay, which is not there in the case in the assumptions of the ideal gases, where we considered gas as only point particles. It doesn't have any volume at all. Okay. Here the gases are basically hard spheres with finite size. Second assumption is two particle close range will interact. Okay, so two particles at close range with interact. So that basically, since the interaction is there, so it basically affects the pressure that is exerted by the total gas. That will have also have been changed from the previous expression of the ideal gases, right? And here they also consider the collisions as perfectly elastic collisions. Okay. And by doing all of this, by taking all of these considerations, we end up with the empirical law of gas equation, or state of the gas equation, and that empirical law is given by E plus A by V squared by V minus B into RP. Okay. These terms basically comes due to the pressure correction terms. That is arise due to the intermolecular interaction. Okay. Intermolecular interactions. Okay. And this is the correction of the volume correction. Okay. That basically arise due to the finite size of the gas molecule. Okay. Finite size of gas molecules. Okay. These are the expressions. So now, so also Van der Waals also derived what is the expression of A and D also. Okay. So mathematically actually calculated. Okay. So this reduced volume, that is what he has done is that he calculated the let's start from the volume part, this part actually. So what you have considered that, so what you have calculated is that average volume available for each of the n particles. That average volume V bar is basically given by the total volume V minus B, where B is nothing but 4 into N into Vm. Vm is nothing but the volume of one molecule. Okay, volume of a single molecule. Okay. Yeah, so this is the volume of the container. Okay. So if you subtract it with the B, this gives you basically the total volume that is available for each of the molecule of the particles. So, similar way, uh, in the container, when there is these gas molecules are well distributed in this container. So what happens inside the gas molecules? All the forces that are experienced by a molecule inside of the gas containers is basically balanced. Okay, so each of the force component basically cancels each other. So it will each of the molecule will face a balanced force. Okay, so it will face a balanced force. Okay. So that means the inside this container, the the pressure that is exerted is basically as a fixed value, and that is nothing but the ideal pressure. Okay, the pressure of the ideal gases. Okay. But the molecules which are closer to the wall of the container, the scenario will be different. Okay, so it will face asymmetric force. Okay, so on a certain direction it will only force. Okay, because other direction is basically blocked by the wall, right? So because of that, for these molecules that is near to the wall, the reduced pressure is basically equal to P ideal minus delta P. Delta P is the reduced pressure. Okay, and now from here you can write P ideal as P plus delta P. Okay, so now delta P, he has calculated the expression of delta P. Delta P's expression is basically A by V square. Okay, so now we know from the ideal gas that P ideal into V ideal equal to nRT, right? Now from here, from this equation, you can write V ideal is basically V bar, sorry, V bar equal to, V bar equal to V minus B. So V minus B, E ideal expression you have calculated, that is E plus n square. So for n mole of gas, there will be n square multiplied, n square by a square by b square into V minus n. Okay, into Ni. So this is basically known as the van der Waals equation. Van der Waals equation for ideal gas. For ideal. So now here, so this is the way van der Waals would be calculated the equation. So this is a basically purely empirical equation. So these equations basically, this relations, the state equation basically able to explain the ideal behavior of gas in a much more accurate way. Okay, and also one thing I forgot to mention is that there is a one important relationship is there, where this V is basically known as the co-volume. Okay, this V, there is a relation between this B and the critical volume. Okay, that relation is basically given by B into equal to Vc by G. Okay, this is also a very important relation that will be helpful for the numerical problem. So this Vc is basically the critical volume that we have discussed in the previous the description, right? This Vc thing. Okay. So now we got everything, almost everything to solve some numerical problems. Okay, so you got the ideal, you get the van der Waals gas equation. We got what is the expression of this co-volume, and what is the expression of this correction in the pressure term. And from the previous discussions, we got the specific heat. We got a very accurate description of the specific heat that is basically given by device. Okay, and by using all of this, we'll be solving some numerical problems. Okay. So now, okay. So first problem, if the Einstein temperature the Einstein temperature of a material is 70 Kelvin, then compute the value of CV at a temperature 50 Kelvin using Einstein's formula. Given R equal to 8.32 Joule mole inverse per minute. Okay. And the options are given: option A 21.23, option B 20.76, option C 19.11, option D 25.45. The units are Joule mole inverse per minute per second. Now Einstein formula means here is that we have previously discussed the Einstein formula, right? So that is basically this one, this formula, okay, this one. For general case, not in the not for the extremum cases, okay, for the general cases. So that expression have to use, okay. So here, let me first write the expression. CV equal to CR equal x square to the power x by x minus 1 whole square, where x is basically theta d by t, okay. So x is theta d is nothing but the Einstein temperature, that is 70 Kelvin, and temperature is 50 Kelvin, right? 70 by 50, 7 by 5, that gives by 1.4. Now substitute the things, all the things here, everything you know. CRT into 8.32 into 1.4 square into to the power 1.4 by e to the 0.4 minus 1 whole square. Do the calculation, it will give you 21.23 joule per mole per liquid. Now problem 2 for copper. Debye frequency is given by 7.98 into 10 to the power 12 hertz. Calculate the Debye temperature theta d. Options are option A 339.2, option B is 383.15, option C is 210.1, and option D is 114.8. So each of them are Kelvin. So the answers are, so we know like theta d, we have used the expression of theta d, right? So this is the theta d thing. Okay. This is the theta d. Okay. So we have to use this thing. Okay. So theta d is the device temperature is H nu d by kb. Okay. So H we know is Planck's constant 6.626 into 10 to the power minus 34. The device frequency that is given 7.98 into 10 to the power 12 hertz. And kb we also know 1.38 into 10 to the power minus 23. So all this calculation you'll be getting as theta d as 383.15 Kelvin. Okay. Now question 3 is find the temperature at which the Einstein's frequency is 5 into 10 to the power 12 hertz. Okay. The option C is 240 Kelvin. Option B is 182 Kelvin. Option C is 425 Kelvin, and option D is 320 Kelvin. Okay. So now we calculate this. So yeah, so Einstein, so we know Einstein temperature answer theta is basically Einstein temperature is related with the Einstein frequency H nu E by kb, right? So here the frequency is mentioned, nu is basically 5 into 10 to the power 12 hertz. So theta would be 6.626 into 10 to the power minus 34 into 5 into 10 to the power 12 into the kb is 1.38 into the minus 23. To calculate this theta will give value 240.1. This will be the correct answer. or 2 gram of two oxygen molecules following van der Waals equation, calculate the pressure at which its volume should be 500 cc at temperature of 27 degrees centigrade. So, and the so the const for 1 mole of oxygen, the constants are given where P is 32 cc, A is 13.6 into 10 to the power minus 5, that is an ATM, and R is 0.0821, so it's given in liter atmosphere. Liter atmosphere by Kelvin. And the options are, option A is 6.45 ATM, option B is 1.78 ATM, option C is 5.76, and option D is 3.00. So these are all the things are ATMs. Okay, so first thing is the so you have to write the van der Waals gas equation first, right? So our main goal is to calculate the pressure. To calculate the pressure, first you have to write the van der Waals gas equation. So the van der Waals gas equation looks like this: T equal P plus N squared A by B squared by B minus NB equal to nRT, right? Now here N is the number of moles for 1 mole, N equal to 1. So here the mass of the oxygen is 2 gram, right? So so what you can write, so here we have to convert it in mole, right? So 1 gram, so N equal to has be 2 by 32 moles, right? Because 1 mole of oxygen is basically 32 grams. 2 gram means 2 by 32 moles. So that is basically 1 by 16 mole. Okay. This much amount of mole of oxygen is there. A, B, everything is in cc. Okay, so yeah, B cc, volume is also in cc. B is in cc, volume is also in cc. A is also atmospheric unit. R is also atmospheric unit. So the units are consistent. Temperature you have to use in Kelvin. Okay. Other than that, everything is consistent in units. So we have to write P plus 1 by 16 whole square into A. A is 13.6 into 10 to the power minus 5 divided by 500 square into 500 minus 32 by 16. 32 comes from this B thing, okay, B is 32 cc. Equal to N is 1 by 16 into 0.0821. 0.0821 into so since it's liters, we have to convert it into cc. Okay. Yeah. Cc means centimeter cube, right? So in order to convert this liter into centimeter cube, cc, you have to multiply this with 10 to the power 3, okay, into 300. Now, if you basically calculate, solve this thing, if you like do the algebra and all, okay, you'll be getting E as 3.0918. Okay, that is this basically 3.0. Okay, option. Okay, so this is quite simple enough. So just the units and all you have to be a bit careful about. What are the units that is given in the problem and what are the units that you are using for your benefit, okay? Or what are the units that has been asked in the options, okay? That you have to be really careful about. Yeah. Okay. Now we will be doing the question number 5. Question number 5 states for 1 mole of helium critical volume is 70.2 into 10 to the power minus 6 meter cube per mole inverse of flow. Calculate the molecular diameter of helium. Calculate the molecular diameter of the helium. The options are A 1.3 angstrom, option B 1.6 angstrom, option C 2.6 angstrom, option D 5.2 angstrom. Okay. Now here, so previously I've discussed, right? So there is a relation between this co-volume V and the critical volume VC, right? So this was the relations that we have discussed. Okay, this relation. Okay. So you have to use this relation basically. So since the co-volume is not mentioned directly, instead this critical volume is given. So you have to use that one only. So B equal to VC by 3. So VC is 70.2 into 10 to the minus 6. So it will become 70.2 into 10 to the power minus 6 by 3. So 23.4 into 23.4 into 10 to the power minus 6 meter cube mole inverse. Okay, that would be the co-volume. Okay, and you will also discuss the co-volume is related to the volume of the each molecule, right? So this was the relation. Okay, But volume V is basically related to the 3 4 into n to Vm. Vm is the molecule of single molecule, a volume of a single molecule. So now, so B is now for n molecule, it's like 4 for n mole of gas, so it would be 4n into Na. Since n mole of gas contains n into Na number of molecules, so n into Na into Vm, right? So now Vm will be equal to 4 into n into Na by, okay, so Vm is nothing but 4 by 3 pi r cube, right? So that means R we can write as 3b by 16 pi mu Na to the power 1 by 3. Now everything is mentioned here. The critical volume B is mentioned. 1 mole, it's for 1 mole. Yeah, so this n is 1. So n is 1. B we know is I've calculated 23.4. Yeah, 23.4 into 10 to the power minus 6. And Na we know Avogadro number. So if you put everything here, you will be getting R would be around 1.32 angstrom. Okay, you will be getting something in terms of meter definitely, but if you convert it into the angstrom, it will become 1.38 angstrom. Okay, so the answer would be option A. Okay. Well, it's actually diameter is mentioned. Oh, sorry. So this is the radius we got. So diameter would be D. It would be 2 into R. Okay, so 2.64 angstrom. Okay, so so this is not be the correct answer. Okay, so the correct answer would be it's the 2.64. So 2.6 option C. Yeah. Okay. Now we move to question number 6. Question number 6 is at 600 Kelvin. Sorry, at 300 Kelvin, 1 mole of hydrogen occupies a volume of 10 to the power minus 3 meter cube. Okay. Find the presence of the gas at 300 Kelvin, assuming it to be a real gas and A equal to 0.024 Newton meter to the power 4 mole to the power minus 2, and B is 2.26 into 10 to the power minus 5 into meter cube mole inverse. Find the pressure. Okay, so you have to calculate basically the pressure. Okay, so similarly, so here also the options are given. Okay, so option C is 25, B is 15, C is 18, then D is 38. Okay, all of these are equal. Similarly, here also you have to use the gas equation of Van der Waals, right? So this is kind of looks like this. If you write in terms of pressure, it will become like this: P equal to RT by V minus B minus V by V square. Just put everything mentioned. So R you know 8.31, T you know 300 Kelvin, volume you know 10 to the power minus 3. Yeah, volume is 10 to the power minus 3 cube. Minus B is mentioned 2.26. 2.26 into 10 to the minus 5 minus A is also mentioned 0.024, yeah, 0.024, and V square, that is 10 to the power minus 3 whole square. This is the expression, this is the value of the pressure V. So pressure, if you calculate, it will give something like this: 2.53 into 10 to the power minus 6 Newton per meter square. If you convert it into the ATM, it will become 24.97 ATM. Okay. The correct answer would be option A, that is the ATM. This is the easy way. Okay, so just you have the Vander's equation, just substitute the things that is given in the proper equation. Now problem 7. For a solid, the debate temperature is, that is theta d, is 500 Kelvin. Okay. Calculate specific heat at a temperature equal to 50 Kelvin, assuming low temperature behavior. Okay. So you have to basically approximate the Dewey's expression that is valid for low temperature. Okay. So that expression you have to use. Okay. Given R equal to 8.314 inverse. The option are option A, 2.85, option B, 3.15, option C, 1.94, option D, 9.73. The units are Joule, mole inverse, Kelvin. So to answer the question, we have to use the Dewey's law, that is for low temperature, right? So low temperature we have already defined. It's related with T to the power cube, right? T to the power cube law. But the exact expression looks like this. Okay. So this expression you have to use. Since you can see in the problem also, the temperature is 50 Kelvin and the Dewey's temperature 500 Kelvin. So you can see the temperature we are measuring is much smaller than the theta d. So in that for that reason actually we are considering this low temperature case. Okay. So the CV expression is now reduced. So reduced expression. So the reduced expression looks like this: CV equal to 4 pi to the power 4 pi 3r into T by theta d whole cube. Okay. Now it's easy. Just T is, we know, T is 50 Kelvin and theta d is 500 Kelvin. Okay. R and pi you already know. So just substitute these things here. If you do that, the expression of CV will be getting as 1.944 Joule per mole of Kelvin. Okay, so now the next problem is problem number 8. For a certain metal, the velocity of the longitudinal waves is half the velocity of transverse wave. What is the D-base frequency? What is the D-base frequency if the number of atoms per meter cube, that means the number density basically, the number of atoms per meter cube is given by 8 into 10 to the power 29, and the velocity of transverse wave is, that means CT is given by 3 kilometer per second. So for solving this problem, we already know there's expression, right? We have derived the expression where this D-base frequency basically related with the transverse and longitudinal wave, right? So that expression is basically given by this nu, if nu d is the D-base frequency, so nu d cube is basically 9n, n is the number density of n. 4 pi into 1 by CL, that is the velocity of longitudinal wave, 2 into CT cube, that is the velocity of transverse wave. Okay, so this was the expression. Okay, now here the longitudinal has half of what transverse has, that is CT by 2, and CT is 3 kilometer per second, that is 3000 meter per second. So CL would be 1500 meter per second, and CT is 300 meter per second, right? N by Vn, that is basically the density per unit volume, is 8 into 10 to the power 29. Okay, so all of the things you got here, right? So just substitute all of the things here in this expression. If you do that, you will get nu d as 9 into 8 into so there is 2 into 2, so it becomes 8 into 10 to the power 29 into 300 to the power q divided by 4 pi into 8 plus 2 to the power 1 by 3. So if you do the calculation, you will be getting nu d as 1.156 into 10 to the power 13 bars. Okay, so this will be the what is this called, D-base frequency for this problem. Okay. Next problem, problem number 9. Primitive cubic crystal has lattice parameter of 0.3 nanometer. Okay, and Debye temperature is 100 Kelvin. Estimate the speed of sound inside the crystal. So estimate the speed of sound inside the crystal. Okay. The options are Option A is 917.65. Option B is 1174.32. Option C is 1007.19, and option D is 602.12. All of the units are meter by second. Okay. So now if you do that, so here since it's a cubic crystal, so due to the symmetry of the problem, what we can consider is that the velocity of the sound, both in transverse direction as well as the longitudinal direction, would be equal to each other. Okay, so you can take Cn equal to Ct. This is due to the symmetry of the problem. Okay. This approximation we have taken into account. If you do that, in that case, this nu d expression, so nu d you already know, nu d is the frequency. Although you have to calculate the speed, so first what you have to do, so you can calculate the speed. So before that, we first calculate this nu d. Okay, from the nu d itself, we will calculate the speed of the sound. Okay, so nu d is basically nu d cube we know is basically 9n into 4 pi into 1 by, let's consider CL equal to CT equal to C, 1 by CQ plus 2 by CQ. Okay. Now if you do the calculation, it will become 9n into 4 pi into 3 into CQ into it would become Cn CQ by, sorry, yeah, Cn CQ by 45, yeah. Now, so you have to calculate now the angular velocity or the velocity of the sound. Okay, so now we know velocity is related to the frequency using this relation v equal to 2 pi mu, right? In this case, it will be nu d. So, so now from here, angular frequency is related. So, yeah. Okay. So now from here you can write v cube as 2 pi nu d cube. Now from here it would become 6 pi 6n pi square cn cube, sorry, c cube. If you basically substitute this thing here, it will become 6 pi 6n pi square c cube. Now from here c cube will now become 2 pi. We know the expression of nu d, right? That is kb theta d by t. Okay. So if you substitute this thing here, so everything will become c cube. So c we can write as kb theta d by h cut into 6 pi square n by 1 by 2. So n basically is there. Now this density of gas is basically, this density is related to the lattice parameter. So n is basically 1 by eq. Okay. So if you substitute this thing here, so it will become kb theta d by a into h squared 6 pi square by 1 by 3. If we substitute everything here, so 1.38 into 10 to the power minus 23 into 100 into 0.3 into 10 to the minus 9 into 5. Now in the denominator, if you substitute the other constant 6 to 6 into minus 34 into 6 pi square. Okay. So now, after doing all of this thing, you'll be getting the c, the velocity as 1007.19. Okay, this is the way to solve this problem. Okay, so basically, we have to equate this quantity with this quantity. Okay, like the nu d with the velocity of the sound. From that, you'll be getting the expression. Okay, so this is it. So this is the last problem for today's discussion. If you don't have any problem, any issue, then we can stop the meeting. Or if you have any question, you can ask. So I am stopping the meeting now.